Hello and greetings. This is a group 4 presenting for the automated assembly project, which is for our selected product, the generic multi-plug. So for the objectives of this project, we wish to achieve three objectives. Firstly, to apply the theory on automated assembly in the implementation of a hypothetical product assembly. Secondly, to design and optimize the assembly process with a carefully planned out redesign and documentation of the robotic assembly processes for the modified product, and to account for and justify the feasibility of the proposed design with safety systems design, cycle time analysis, and financial justification. So for the work distribution, project plan, and milestones, we have a few packs of tasks. Initially, our project started off with everybody doing the first task, which is modeling the existing parts in 3D modeling software. And eventually, we divided the following tasks amongst us equally, which is first task pack by me, which is the designing of feeders and fixtures, design the robotic cell layout, and financial justification. Secondly, by Zane, which is the selection and design of gripper, selection of robot, and safety system design. And by Henry, study all assembly process layout and timing requirements. We design the component and conduct the cycle time analysis. Our milestones, as seen in the Gantt chart here, we formed our group. Our topic was selected, and we distributed jobs in the first week, and everything was done in the first week except for the job distribution we done in the second week. We modeled the existing parts the following week. We completed in week 3, and afterwards we designed the feeders and fixtures, designed the robotic cell layout and other tasks as planned. Somehow we encountered a bit of delay due to changes in modification and design considerations. In overall, including the robotic cell, the robotic arm, and whatnot. So there were some delays as expected. Okay, so for the typical assembly process, current assembly practice in Malaysia, in general, Malaysian manufacturers, who also are electronics product manufacturer, they assemble and produce these products manually. As you can see, this is one of the manufacturers in Malaysia, and this is the 3D modeling of the original model in exploded view, the casing, the cover, and the overall product. So during the assembly, we laid out the parts when we dismantled them in this order, and we followed the sequence as shown here in the table to assemble back the product. So by average, we had a total time of 2 minutes and 51 seconds to assemble it. Okay, so for the automation feasibility, I would like to pass to Henry.
Right, thank you, Sheldon.
Okay.
I'll stop the slides.
The slides?
Yeah, it's not moving on my side.
Oh, really?
Yes.
One moment. Is it?
It's stuck on the 3D modeling side.
Oh.
For me, it is moving.
Right, it's moving now. Right.
Okay. Okay, right.
Okay, so I'll take the project feasibility part. And with status, we had a proper redesign on all the parts and plan out how do we wanted the automation process to go on, and we have the design accordingly. Depends on the process and the step-by-step movement of the robot, taking into consideration. We also minimize the human error and try to eliminate it, but somehow we still have some teeny problems that won't matter the process itself. And the hoppability and stackability of with the other criteria of the components are reconsidered in the process of planning and remodeling, but most of the problem are solved. So next.
All right.
So we go on to proceed on the parts redesign and remodel. Let's go to the next slide.
Okay. Okay. I think this is my part. Okay.
No.
Huh? Oh, you want to?
The 3D model slide.
Oh. Okay. It's not changing?
Yes.
I think.
Yes,
Okay.
it's changing now. Right. From the right side, you guys can see all the remodeled parts. As you can see from the top, you can see that the earlier fuse hole that is supposedly facing the top is swapped to the side, as the red colored new fuse cover is installed, and we have the pins that holds the fuse changed in directions, as well as we have the isolators cut out for the space needed for the fuse. Other than that, the safety caps that is used in the whole casing are changed and to save up the parts and use of the spring. Other than that, we have remodeled the whole light indicator in this system. We replaced the LED light bulb with a module that is solid, which can be fixed on the case tighter and safely and easy and more easy assembled by the robot. We also removed the screws from this whole system and we replaced it with hooks and notches on the side of the casing. So it will save up a lot of time on the assembly part. I'll pass the rest to Shazwan.
All right. Okay. Thank you.
He'll talk about the feeders.
All right. For the feeders, basically we're using 4 types of feeders: the vibratory ball feeders, the magazine feeders, the tape feeders, and conveyor system. So for the feeders, the first type, which is the vibratory ball feeders, we are transporting the parts of the casing, which can be seen on this right side here. This is for the main casing. This is for the case cover. And these are for the pins that can be flattened on one side at least. So we are using gravimetric principles to actually make them fall down into the slots. Here we're using deflectors to ensure the casing come in the correct orientation, and some slots or traps to keep the orientation or the opening upwards. So the ones facing downwards will be thrown out of the track. For the tape feeders, it's on the opposing sides of the jig, so it houses the fuses and the fuse cover. So in the assembly process, which is in the final stage, the fuse will come into the fuse cover first before being transported onto the main case, which will be tilted on its side by 90 degrees, which we will see later, which makes it easier to enter the case, to be inserted into the casing easier, rather than the casing being on its side. So for magazine feeders, we are feeding the 2 variants of the safety caps, the pin isolator and the LED module. We are utilizing the magazine feeders for this one due to its stackability attributes, where most of the surface on each side has a considerable amount of surface contact, as we can see here. The mechanism is it comes in pairs, so one magazine feeder set will have a tray and catchment tray in front of it, so one will slide down and will be transported to the encatchment tray, where will be the contact point for the robot to pick it up. Next will be, or finally will be, the conveyors or the pallet trays. The conveyors will convey the trays from the intake point to the receiving conveyor. And at the receiving conveyor, the robot will pick up the parts one by one until it's finished, and then it will exit the cell through the exit conveyor. It will be transported to the next track of cell using a piston, a hydraulic piston, sorry. Yeah. Same, this for the neutral pin and prong, and the one previously was for the live prongs. Okay. So for the selection of robot, I'd like to pass to Zain.
Thank you so much, Shazwan. So as you know that we were doing the assembly for the generic plug, for that the selection of the robot was very important, and for the selection of robot the payload value is the foremost attribute we'll look into. The payload value we were looking was more than 3 kgs. Uh, and then the next attribute we wanted was the maximum and the minimum range, because 11 components were being assembled. So we didn't want to jumble everything up. So we wanted everything to be sorted perfectly. That is why the range we were looking was more than 800 millimeters. After the consideration and everything, we came up with the robot that is ABB IRB 1200. 5 is the pay value, and 0.9 is that it can reach 900 millimeters, and it has a 340-degree turn axis, which means that it can easily grab the components from its back. Next, please. So for the robotic assembly cell, there are a total of 4 vibratory feeders being used, 2 tape feeders that I'll be discussing in the later part of the presentation, that are placed just next to the jig, 6 conveyors total, and 4 sets of magazine feeders. Like in one set there are 2 magazine feeders, so 4 sets in total, 8 magazine feeders are being used. Next, please, Shazwan. Okay. So, Shazwan, I'll be needing your help, please, for this. For the basic layout, the robot-centered work layout has been considered. Everything, the robot has been placed in the center, and it can approach everything within its radius. So, as you can see, there are.
One moment. Point. Okay. Continue.
As you can see that there are 4 vibratory ball feeders that are bringing in 4 different components. 2 of them, like all of them, have the same diameter, but the outlet lane has been altered. 2 of them have 50 millimeter outlet lane, and 2 of them have 80 millimeters. Then there are 2 tape feeders that are bringing in the fuse and the fuse covers that are placed just next to either side of the jig. In the center there is jig, then in the X that's the robot. Then on the either side of the robot you can see that there are 6 different conveyors that are bringing in the parts, as it was explained by Shazwan earlier that how it will work. So these are the 6 conveyors, and just behind the robot there are 8 magazine feeders that are being used, and the ball feeders are kept away from the reach to prevent reach of the robot, to prevent any mishap or any accident from happening. And it's like zone 1. I'll go into the safety design now. Zone 1, it has no assembly related machinery there or mechanism. There's nothing placed there for safety purposes, and the personnel or the workers, they can roam there, they can like walk there freely, and for that they don't need any authorization or anything. For the zone 2, there is this IRC5 controller cabinet placed that is responsible for the robot to work, and that is placed in zone 2. And mostly the replenishable feeders, they are inside the zone 2 area. like the magazine feeders and the tape feeders that are bringing there's a drum and bringing everything that is being placed in zone 2. And the entire zone 2 is enveloped by a physical barrier. There is a physical barrier uh, which might be a mesh gate with entry gates located at 3 points. And in zone 3, the assembly area reachable by the robot arm is bordered. It is bordered by the tape, like the Hezit tape, the black and yellow one. And I'm sorry. As mentioned earlier, the robot arm itself, the escapement of the vibratory bowl feeders, the tape feeders, the tray, and everything, it's away from the reach of the robot. Next, please.
Okay, I'd like to add, Zain, if
Yeah,
you may. Yeah, the rationale of placing the emergency stop buttons is to control the movement of the robot when it's moving out of expectation. Over here, whenever a technician is working on the IRC5 controller, if there's some unexpected movement happening in this area and a personnel might be affected, the emergency stop button here would be able to stop it immediately. And these emergency button placements are rationalized where when one personnel is working within this area in close proximity to the robot arm, the emergency stop buttons are within reach by another personnel that might be accompanying the person to actually stop the robot from moving. Okay. Sorry, next gripper design. Yeah.
So
okay, next
to select gripper. So as we had 11 different parts, all parts varied in size and in weight. So we wanted to come up with the efficient gripper that might work with it. So the initial requirement for the stroke per jaw, that is the opening of the gripper, we wanted to go more, it should be more than 80 millimeters. So and it should be electric because we had, as I said, that we had different sizes and different objects, so we needed to exert different kind of forces for every object. So we came up with EGL 90 CN, that is by Shank. The closing time is almost around 0.7 seconds. The workpiece weight at a time, it's 3 kgs, and stroke per jaw, it's 42.5. That is, in total, it's almost around 85 millimeters. Next, please. So in order to pick all the different objects in which varied in size and weight, there were cylindrical, there were flat objects, and there was square. So we came up with the design that we can accommodate all the shapes and all the objects with this finger. So this finger, as you can see, it has a small extrusion at the back of the finger, which is responsible to pick the cases, the back cases and the front cases from inside of the wall. This extrusion is for the back case, which helps to pick it up from inside. And the circular arc, you can see, it is for the cylindrical objects such as the fuse, or even for picking up the fuse with the fuse cover. And mostly the finger is flat and it accommodates every object. It will be seen in the later part of the presentation. Next, please. As you can see that once we had to pick up all the objects and had to place it, mainly the cases, we had to place it into the jig, and then all the components and all the parts have to be pushed inside by the robotic finger. So this is how we are picking up the objects, and then we are placing it differently. Next, please. This is the back cases, and this is the safety cap. Then this is fuse cover, and then LED module. Next, please. Then there are these pins, the isolator, and everything. We were able to pick it up because the fingers are kept to be very narrow because it has to go inside the cases in order to fit all the objects properly inside. Next, please. Now I would like to hand over the presentation to Henry for the cycle time analysis.
Henry?
Henry?
Henry, are you there? Oh my God.
And
Henry?
Henry, your part on the present. Yeah, sure. Shazwan, can you take him in? He's disconnected.
Oh, I see. Oh my God.
Yeah, just take him in.
Yeah, sorry. One moment. I think his internet is slow.
Yeah. We're sorry, Dr. Hoodie.
I'm back.
Yeah.
So I'll take over the robotic arm speed part. As we can see from the datasheet from the robot, we are able to find out the max speed of the robot turning. So all we have to do is we find out all the degrees we needed using the inverse kinematics function. So we found out all the angles of the axis of the robot on each of the gesture when we are picking up all the parts, and using that we can distinct the change in angle, and we can use that to find out the time needed for the robot to move around. So next slide.
Sorry.
So from these two pictures, we are showing that we are able to get the distance of all the placement from the layout itself. When this is where we get all the distance, and we sub in for the inverse kinematics function and find out all the angles. We also use the top view and to find out all the turning angles of the robot all around the plane, and use that to take out some data using the, how do I say, we measured the time needed to turn that angle, right? So next, in this next slide, we have all the detailed saying that which part is coming from which feeders, and we have it stated more detail on like which part comes from which feeders and goes to the jig, and how we treated the parts, as well as the time taken for the robot to perform that whole step and action. So most of that have the time included of the robot gripping the object and traveling all around the layout, and then placing it on the place it should be. So as for some of the parts that is coming from same feeders, they have a slight time variant, but we have it solved by having all the feeders lying on the same lateral face. So we have a slightly more constant timing, and the whole process takes about 45.84 seconds for the robot to perform the whole assembly from start to end. I'll pass the rest to Chazwan.
Thank you, Henry. So for the financial and economic justification, for the variables that we need to use to calculate the payback period and the return of investment, first we see the cost here. So the costing is we utilize reference prices for the ones that weren't quoted directly. For example, a range of prices. So we took an average of it, and a reference price that's where we have a lack of information. We use a price of a product is similar to the item. Items that are items such as the magazine feeder, where there's no, where there's usually customization, we utilize the mass used up by the magazine feeders, and we quantified it in terms of cost per unit in kg in this terms, and we use that as the cost for the items. And the custom finger set same goes to the robot gripper set. With this estimation, we included the markup as the which includes the fabrication costs and whatnot. And from this total, we found the cost to be this amount: 366,263 ringgit and 68 cents, which account for 85% of the cost. So according to the lecture slides, we found that these costs cover 85%. So the remaining 15% are related to installation, which is the common distribution of prices. So with this, we found the total cost to be 430,898 ringgit 45 cents. For tax credit, we utilize the credit rate by default assumption of 10%. So from that, we got the tax credit at 43,089 ringgit and 85 cents. For the annual share of workers that shall be laid off from the installation of this assembly cell, we got this figure from a website which cites the average worker's salary for the manufacturing industry. So the layoff expectedly for one line would be one foreman and 4 line workers, as we can see from the photo as a reference in the previous part that I've explained. So the annual payout would amount to 186,360 ringgit. And the productivity savings from this layoff include the fringe benefits. So we accounted for 5% of the annual payout to be the cost, and it comes to 9,318 ringgit. For the robot depreciation value per year, we use the straight line method to quantify the depreciation value per annum. So the method is to find the difference between the total cost and the salvage value, and divide it by assumably a tax life of 7 years. And we found the depreciation value to be 55,401 ringgit and 17 cents per year. As for maintenance of the new system, we accounted for the robots parts, where the relay of the controllers, the PLC cable, and the motors for the robots, robot axis, replacement for the respective frequency cycle per year. So by standard, we would say 1 man hour would be 1 month. As we say, we can say the frequency would come up to 12 man hours a year. So 1 man hour a year would mean annually, and the replacement are done according to requirements. In the case of the relay and the PLC, it's the maximum number of replacements that can be done. And the motor, assuming an ideal case, we assume up to 3 half of the robot's actuators replaced in a year. So the total cost of replacement or maintenance of the procurement of the supply parts would be 4,947 ringgit 41 cents. As for the staffing, we are using the same source for the average wages. So in terms of staffing costs, we assume that the operator, the technician, and the supervisor would be employed year-round, whereas the programmer would be on a periodical basis, as the robot reprogramming would need as much frequency as it would the other personnel. So we took an estimation of 3 months. So in terms of this, prorated annual payout will have a cost of 177,420 ringgit, plus fringe benefits. The total annual payout for the staffing would be 186,291 ringgit. So to calculate the payback period, use the formula, which is the ratio of total cost, the net cost, which is the cost minus the tax credit, and then the savings that we have from the installation of the robot, and the difference and its difference with the other costs that comes with it, which is the maintenance and the staffing. Overall, we find the payback period to be 6.481 years, or 6.5 years, which is longer than average payback period or optimal payback period, which is 2.5 years. So as for return on investment, assuming a 20-year lifespan, as suggested by the manufacturer ABB on their robots, which is somewhat of a indirect guarantee of 20 years. So using the formula, we found that per annum, they would have their return of investment of about 9.875% annually. So from the justification, we found out that the return of investment percentage per annum is quite substantial, but the payback period is more than expected. So as you can see here, this is the summary. Finally, for the conclusion and recommendations, I pass to Henry, is it? Henry or Zain? Zain, yeah. So Zain.
Thank you so much, Shazwan. Our research and with the project we did, we found out that the feasibility of designing the grip, of designing the fingers, feeders, fixers, and everything, and choosing the robot, and basically automating the assembly is fully justified. Then for the safety system, we designed it in such a way that we can avoid any accidents from happening or incidents from happening. The time that was being taken to assemble when 2 minutes 51 seconds, it has been reduced to 49. That is a 60 to 70% decrease in time. And lastly, as it was described by Shazwan, that the return on investment is huge compared to the other return on investments. And the payback period, it's a bit off. Like it should be less than 2.5 years or 2 years, but for us, it's 6.481 years, which is longer than the optimal period. That's all, I guess. Thank you.
Thank you
very much.